Hi guys, today we're starting a new topic of statistics again. We're going back and visiting, but we're going to look at a new measure of how to compare data. So first of all, we already have some ways to compare data, and you should have been practicing median and mean in the first lesson, and we'll use the median later, probably next week. But today we're going to use the mean first of all to start us off on our new formula, which we're going to use, which is the formula that works out the standard deviation. And once we've shown you how to work out the standard deviation, I'll talk a wee bit more about what that actually shows you. So first of all, here's a set of data that I've just made up. It could be like scores for a team or something like that. So before we do anything else, when we start with the standard deviation, the first thing we do is we work out the mean. Sometimes you're prompted to do that in a part A of the question. So up until now, you might not recognise this notation. Some teachers teach it in first year and some don't. So mean, another notation that we can use for the mean is something we write as x with a little line on top of it, which we call x bar. So if you write an x bar, any mathematician would recognise that to mean the mean, okay? Now to work out the mean, again, you should have revised this already. You then take the set of data, you take each data point, you add them all together, and then you divide them by however many pieces of data there are. So in this case, there was 1, 2, 3, 4, 5. And when you do that, I've made it into a nice straightforward whole number. You won't always get whole numbers, but I've just made it quite easy to start with, okay? So our mean for this set of data is 20. Standard deviation, a new formula. Now, it looks a wee bit complex. You get this formula on your formula sheet in the exam, so you don't need to worry about memorising it. I would always make sure that I would go back and double check it, even if you're confident with it on the day of an exam. So it does look quite complicated. Don't panic, because once we break it down a wee bit, it's actually quite straightforward. So you should recognise already the square root sign. It's across the whole thing. So the last thing we're going to do is take the square root. Here, this is a new sign here. This is a sign that represents to sum. So basically, it's just going to tell us that at some point we're going to add some things together. Because in mathematics, when we sum things, we add them. Okay? We'll get to that once we start to work into our formula. X, in this case, here it is here, it just represents all the different pieces of data. So at some point, we're going to use each piece of data to do something. So we know what X is. It represents these 5 different bits of data in this case. X bar, we've already spoken about, is just the mean. And the only other thing in this formula that you won't recognise possibly is n. Now you might already recognise it because n, when we're talking about these statistics, is really just talking about the number of data. So you might have written that down when you were doing a stem and leaf diagram. At the end of your stem and leaf diagram, you should write also at the bottom n equals and list however many data there are, number of data points. Okay. So all this formula is really asking us to do is take each piece of data, which is your x, we're going to subtract from that x bar, which is the mean. Once we've done that, we're going to take the answer to that and we're going to square it. Once we've done that for each piece of data up here, we're then going to add them all together. We're going to sum them. Once we've gotten that total sum, we're going to divide the whole thing by the number of data, take away 1, and then we take the square root of the answer at the end, and that gives us a new value, okay? Now, the best way to do this, if we're using this formula, is we're going to use a table. And if you can't remember the headings in the table, really go back to this formula. Once you've practiced it, this should hopefully prompt you. So first thing we need to do is list each piece of data. So go back up to your list. I generally try to list them in order because I tend to find then I can spot any silly numerical mistakes that I make either with a calculator, if this is in a calculator paper, and quite often at the moment it's showing up non-calculator with quite straightforward numbers. But we'll look at some of those examples later in the week into next week. So we're going to take each piece of data and we're going to subtract the mean from it. So that's the first kind of column we're going to work out in our table. Now, you don't need to show the working, I'm just going to show you for the first one what I mean by this. I'm taking my piece of data, which the first one is 18, and I'm going to subtract 20 from it, because that's what the mean is for this set of data. So 18 take away 20 is just -2. Now, it might be worthwhile then working across the page. If you're using a calculator, if these numbers are quite large or awkward, you might want to work across the columns here, because then what we're going to do is we're going to put this into effect and we're going to square the data. So if you've got awkward numbers, say this mean wasn't a whole number, so you're taking something and subtracting a decimal from it, you would definitely want to use your calculator to then square it. So you might want to work across the table here. The other thing about this is then, when you square this, it should not give you any negative numbers in this column. And that's quite a big mistake that can get made here. So watch out for that. If you use your calculator and work across in a calculator paper, it should avoid that for you. So here I'm not going to write them all out. 19 take away 20 is just minus 1, which I square it, be careful, minus 1 squared is 1. 20 take away 20 is 0, 0 squared is still 0. 21 take away 20 is just 1, which when I square it is 1. And 22 take away 20 is just going to be 2 squared is giving you 4. Okay, so there's our table completed. Now there's a couple of things you need to do here. One of them you can do as a check, which is really to add this column together, and it should then come to 0. So you can see I've got a minus 2 plus, and a minus 1, which gives you minus 3, plus 1 plus 2 is going to cancel out and give you 0. Now, the only reason that column wouldn't come to 0 is if the mean had been a really awkward number and you'd had to round it, and then when you start to take away here, you would end up possibly losing that, and you would end up with something close to 0. In this column, again, please note you should be looking out for making sure that you have absolutely no negative values in this column, because when you square all of these, even if they were negative, they become positive. And then when you add them all together, which is the last bit we're going to do, we're going to sum, which means to add. We're going to have 4 plus 1 plus 1 plus 4, which is just going to give us a nice 10. Okay, so now we've got everything we need to work out the standard deviation. I'll just squish it over here. So the standard deviation from that formula further up, the top line, I have just worked it out. To add all together, each piece of data with the mean taken away, all squared, is 10. So that's what we get from doing all that work in the table. Divided by n minus 1, the number of data in this original data set, there was 5 bits of data. So we're going to say 5 minus 1. Now just be careful with your calculator now and make sure you do everything before you take the square root. So I'm going to go 10 divided by, and if I just work out 5 take away 1 is just 4. So I'm going to go 10 divided by 4 equals, and then just do the square root of that answer, and I'm getting that. Quite often they'll ask you to do it to maybe 1 or 2 decimal places, so in this case it's not asking, I'll just round it logically to a couple of decimal places. Looks quite sensible. Okay, so there's the standard deviation. Now, what does the standard deviation actually mean? It just looks like a bit of a random number just now. So what we're going to do is we're going to compare that to a different data set, and then that might allow us to see what the standard deviation actually is representing. So I have done a different set of data, and instead of working all through it, I'm going to just talk you through it again. So here I've got a totally different set of scores. Maybe compare them to the scores that we started with. So we started off with a 20, 21. So all these things worked out to have a mean of 20, and they were all quite close to 20 when you look at them. Okay, let's look at this data set. Now, I've purposely made this data set work out to have a mean of 20 as well. But if you look at this set of data, I hope you can see that it's not the same as that data set we had, which was all close to 20. This one's quite spread out, so if the mean of the average here is 20, there's some points that are quite far away from 20. Even the 27 is quite far away, the 14, it's only the 19 that's quite close to that mean, okay? So if we follow through with this formula again, so the first thing I do, I've listed all the data, I've listed them in order this time. Then I've taken the mean away from each, so 2 take away 20 is minus 18, and this is where I've worked across the page and I've squared that as I went. 14 take away 20 is minus 6, squared is 36. 19 take away 20 is minus 1, squared, and so on. 27, 7, and then when I take 20 away from this and square it, I get another 324. So when I add these together, I get quite a big number this time, and you can see I've also done my check. If I add those 3 negatives together, it comes to the same as these two, so it's negative 25 plus 25, so it's 0, okay? So just because of that, this number here is much bigger than the 10 that we had in the first example, okay? So again, here's our standard deviation. Now, we put that number into the table, we divide it by, I still had the same number of data, I had 5 bits of data, so I then got my calculator, did 734, divided by 4, and I've taken the square root of that, and again I've just rounded it to the same number of decimal places. And I was just then briefly going to talk to you about the difference here. So you can see our standard deviation for this was 1.58, and our standard deviation for this set is a much bigger number of 13.54. And I've written this down here, just if you want to compare them. Here's our set 1. I've made it so that they've got the same mean, and yet the standard deviation is vastly different. So if we think about just plotting this data, right, if I did it on like a scatter graph, right, a little graph here, a wee dot plot, sorry. So if we have 20 here, then if I take that first set of data, one of them was 20, one of them was 21, one of them was 19, one of them was 22, and one of them was 18. Okay, so you can see that that little tiny set of data is really close to the mean. Remember, the mean for both sets of data here was 20. If I plot, sorry, focus is gone. If I plot the second set of data, then it's going to be much more spread out. Okay, so if I go for, what have I got, 27, apologies, it's not really got a scale here, so there's 27-ish, 2 is going to be way down here, 14, somewhere in here, 38, nearly up at 40 there, and then 19 is going to be quite close to that mean, just below it. Okay, so even just from comparing the two sets of data, you would hopefully realise that that data set, the first one, is much less spread out than that second data set is far more spread out. So that's what the standard deviation allows you to see. The bigger the standard deviation, the more the data is spread out from the mean, okay? So sometimes that allows you to say that if this was a set of scores for a team, what you would say is that data set 1, well, they've scored an average of 20 and they've got quite a small standard deviation, so they've performed quite consistently. Whereas data set 2, they still have the same average score in the end, but they're a wee bit all over the place with their scores, and their standard deviation is therefore much bigger. So the standard deviation being larger tells us that that team, if that's what that data represents, has performed much less consistently than the other set of data. Okay, so our standard deviation is a new formula. We need to practice the technique, and then we have to think about how to use it to compare sets of data. And as I say, what it shows us, and you can see that from your little dot plot comparison, clearly that first set of data is much smaller. But if you don't want to do a dot plot, say you've got hundreds of bits of data and your computer calculates a standard deviation for you, if it's a smaller standard deviation, the data set is much more consistent, or if it's a much larger number, a much less consistent set of data. Okay, it's much further away from the mean. Okay, I'll let you go and do some practice now.